My dear students, let me welcome you all to a new edition of physics. In this edition, we'll try to understand the relation between V external of a battery, V internal of a battery, and EMF of the battery. As a matter of fact, external voltage of a battery is called terminal voltage. Internal voltage is also called lost voltage. And we'll try to understand the relation between them. Also, we'll try to answer very important questions relating to this topic. Hopefully you'll benefit from them, so let's get started. The first way is the series connection. In front of you, we've got three resistors connected in series. R1, R2, R3. Okay, connected in series means we've got just one path for the current to flow. One path means one current intensity, okay? So the most important piece of information here, as long as we've got series connection, we've got the same current intensity. So the same current would flow through the resistors. Okay, but potential difference, it depends. It depends on the resistance. So we've got V1 across R1, V2 across V2, and potential difference V3 across, R3. And total potential difference, of course, will be equal to V1 plus V2 plus V3. And from Ohm's law, potential difference is the product of voltage is equal to IR. So V total is equal to IR total. V1 IR1 plus V2 IR2, and V3 is IR3. Same current, as I said, because they are connected in series. The current intensity will be crossed out, so R total equals R1 plus R2 plus R3. And what if the resistors have the same value? Okay, it's all easy. Then R equivalent will be equal to the resistance of just one of them times the number. So N indicates here the number of resistances. This was the first way of connecting resistors. We've got another method to connect them. It is, parallel connection. Okay, in front of you we've got three resistors connected in parallel. Okay, the current here splits. The current entering the parallel group, parallel combination, splits. Okay, I splits into I1, I2, I3. I1 through R1, I2 through R2, and I3 through the resistance R3. And they'll combine to give the same current intensity entering the group. It is denoted by I. And we've got very important piece of information here. Connecting in parallel means we've got the same potential difference. So potential difference across R1 is the same as R2, is the same as R3. It is equal to the total potential difference. So V1 is equal to V2 is equal to V3, and it is equal to V total. This is very important when we are connecting in parallel. Okay, as I said, I is equal to I1 plus I2 plus I3. And now we can say V total is equal to V1, and it is equal to V2, and is equal to V3. Potential is the same. So V over R total is equal to V over R1 plus V over R2 plus V over R3. Voltage will be crossed out, so 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So R total is equal to, R over N. This expression is used when we've got resistors of equal values connected in parallel. The value of one of them R over the number. Okay. relation between V battery, the electromotive force of a cell, and external voltage. Okay, to understand the relation, we have to, mention or to apply Ohm's law to a closed circuit. In front of you, we've got a closed circuit that consists of a cell, V battery, and a resistor. What about the cell? It has got an internal resistance denoted by small r, and the current flowing through the circuit is denoted by capital I. Okay. Definition of electromotive force of a cell is the work done in transferring unit charge, in transferring one coulomb, okay, through the external circuit as well as the internal circuit. The work required, or the voltage to transfer unit charge through the external circuit, is denoted by the external or terminal voltage, and that to transfer through the battery we call it internal voltage or lost voltage, and it is denoted by VIN. So V battery equals V external plus V internal. Yes, any voltage is calculated by the product of current intensity and resistance. So V external is equal to IR capital, V internal is IR small. Small r is the resistance of the battery. So we can say V battery equals I, between two brackets, R capital plus R small. And let me mention something here. I is the current through the battery, the total current. Okay. So R capital is the external resistance of the external elements. R small is the internal resistance of the battery. So once again, current through the battery is calculated from the expression V battery over R capital plus R small. We call this Ohm's law of a closed circuit, and it is used to determine the value of the current passing through the battery. So we can say the current, once again, through the battery is equal to V battery over R equivalent of the whole circuit. Whole circuit means external and internal. V external is also called the terminal voltage, and V internal, as I said, is called the lost voltage. And now we want to know the relation, to understand the relation between EMF of a cell or V battery and terminal voltage and internal voltage. Okay, so we'll perform an activity here. In front of you, we've got a circuit. Okay, your attention please. We've got a battery. EMF of a battery is denoted by VB. Internal resistance is denoted by small r. And we've got a switch and it is closed. Rheostat to change the resistance. Ammeter to measure the current. And we've got something here very important, a voltmeter connected across the battery. Actually, it measures the terminal voltage. It measures terminal voltage or external voltage. Okay. Your attention, please. When the key is opened, okay, when it is opened, no current flows through the battery. Okay, what about the reading of the voltmeter situated across the battery? Okay, it reads maximum value. It reads a value which is equal to V battery. Okay, so terminal voltage is equal to V battery when no current flows. Once again, when the key is opened and no current flows through the battery, the terminal voltage, which is the reading of the voltmeter equals V battery. Why? Because the internal voltage which is calculated using the formula IR small is equal to 0. Current is 0, so the product equals 0. In this particular case, yes, what happens? V external equals V battery. V external is maximum and is equal to V battery when no current flows through the battery. Okay, but since, as I said, V battery equals V external, so we can say V battery is equal to V external plus IR small. So V battery or EMF of a cell will be equal to the external voltage, okay, when the current is equal to 0, simply because IR is equal to 0. Okay. Once again, when the key is closed, so we've got a current that flows through the battery. So the reading on the voltmeter, which reads external voltage, the reading decreases. Reading on the voltmeter decreases because the value of the lost voltage IR small will be increased. It was 0 when the key was open. Now it has got a value. Okay. But if the current flowing in the circuit is decreased, and how to decrease it? By increasing the resistance using the rheostat. What happens to the terminal voltage? The terminal voltage will be increased when the current is decreased. Okay. The terminal voltage increases because the internal voltage, of course, decreases. Once again, V battery, since V battery is equal to V external plus V internal, so V battery is equal to V external plus IR small. So V external is equal to V battery minus IR small. We've got something here important to mention. Yes, your attention please. We've got here a battery and a switch, but no current flows. So the voltmeter across the battery reads, yes, the voltmeter reads V battery, which actually reading terminal voltage, but terminal voltage on this particular case will be equal to V battery. So terminal voltage is a maximum, and when no current flows through the battery, and it is equal to V battery. But it read 0. Voltage across the battery drops to 0 when the battery is short-circuited. What does it mean when it is short-circuited? When it is connected, yes, to a copper wire, thick copper wire of 0 ohmic resistance. So voltage across the battery equals 0 when the battery is short-circuited. That's to say when the battery is connected to a wire of no resistance. We've got a question here. What would happen to the readings on the two voltmeters if the value of R1 was increased? Okay, we'll increase the value of R1. We want you to say what will happen to the readings of voltmeter V1 and that of V2. As a matter of fact, increasing R1 will increase V1, but will decrease V2. So V1 increases, but V2 decreases. And let's explain it. So since the current through the battery is calculated from V battery over R equivalent of the whole circuit, and V battery is constant, of course, so we've got an inverse relation between the current and R total or R equivalent, since V battery is unchanged. Okay, and since V internal is calculated by IR is small, so V internal is proportional to the current, simply because small r is constant. V internal is directly proportional to the current, okay, and the current is inversely proportional to the total resistance. Okay. V battery is equal to V external plus V internal. V battery is constant, so V external plus V internal is equal to a constant, and this means when V external increases, V internal must decrease. Okay. So when V internal decreases, the external voltage increases. Okay, we'll take it from the very beginning. When R1 increases, increase in R1 will increase the total resistance. The current through the battery decreases. Okay, and internal voltage depends on the current. It decreases. When internal voltage decreases, external voltage increases. Okay. And what about the reading of the second voltmeter, V2? It depends on the current, simply because R2 is constant. So it is proportional to the current. What happens to the current? The current decreases, so it decreases. So V2 is proportional to the current, R2 is constant, so when the current decreases, V2 decreases. Further example for explanation of the previous idea, but we'll explain this but using figures, numbers, okay? In front of you, we've got a battery of 12 volt. Okay, V battery is equal to 12 volt. Internal resistance of the battery is equal to 1 ohm. We've got, yes, variable resistance. The value, chosen value is 2 ohm. And by the way, we'll change it instead of 2, it to be 12. Okay, and we've got a resistance of 7 ohm. V2 measures the potential difference across R2. V1 measures the terminal voltage. Okay. R equivalent of the whole circuit, or R total, it is 7 plus 2 plus 1. 1 is the internal, it is 10 ohms. Okay, so the current through the battery equals 20 over 10, it is 2 amperes. V external is calculated from the expression V battery minus IR. So it is equal to 20 minus 2 times 1, it is 18 volt. Keep this figure, this number, yes, keep it on mind. Okay, and what about V2? It is calculated by IR2. It is 2 times 7, it is 14. So terminal voltage 18, voltage across the resistor, the 7 ohm resistor, it is 14. And now we'll change R1 instead of being 2 ohms to be, yes, 12. We'll increase it and we'll see the effect of this on the terminal voltage V1 and on the voltage V2. Okay, total resistance, it is 7 plus 12 plus 1, 20. Current through the battery, V battery over R equivalent, 20 over 20, 1 ampere. Now V1, which is V external, equals V battery minus IR small. 20 minus 1 times 1, it is 19. You remember the previous figure, it was 18, so it increased. V1 increased when we increased the value of R1. And what about V2? It was 14, and now IR2, 1 times 7, it is 7, so it decreased. So increase in R1 will, yes, increase V1, but it will decrease V2. Okay. Another question, what would happen to the readings on the voltmeters if R1 was increased? But in this circuit, in this example, we've got something special here. Internal resistance is equal to 0. So what happens when internal resistance is equal to 0? V1, which is terminal voltage, will be equal to V battery. Okay, V battery changes when we change the battery. We didn't change the battery, so V1 will be constant. It won't be altered. Okay, this is very important. Internal resistance is equal to 0, So V external is constant since it is equal to V battery. What is the effect of increasing R1? Okay, V1 is equal to V battery simply because IR small, V internal is equal to 0. So V1 remains unchanged. And what about V2? V2 is calculated using the formula IR2. Yes, when R1 is increased, by increasing R1, current will be decreased and V2 will be decreased. Okay, V2 is proportional to the current. R2 is constant, of course. So what happens to the current? The current decreases, V2 decreases. Okay. When R1 increases, the current decreases. Okay, so V2 decreases. And what about V1? V1 remains unchanged. Why? Because it is equal to V battery. Why it is equal to V battery? Because the internal resistance is equal to 0. Another question, what would happen to the readings on the voltmeters if R1 was increased? Okay, what about this example? Something very special here. V1 actually is equal to V2 because both of them, yes, measure external or terminal voltage. Okay, there is a trick here, but you are clever enough, you're smart enough to know it. V1 actually is equal to V2. V1 and V2, each one of them is the terminal voltage. Okay, so what happens when R1 is increased? When R1 is increased or when R1 increases, the current, yes, of course, the current decreases through the circuit, of course, decreases. And internal voltage depends on the current, and it is proportional to the current. Current decreases, internal voltage decreases. And when internal voltage decreases, external voltage should increase because the sum of both of them is constant, which is V battery. So V1 increases, and of course V1 is the same as V2, so both of them will increase. Note, we've got something here, something interesting. In the previous circuit, previous example, if R was equal to 0, what if the value of R is equal to 0? And, oh, okay. Then V1, which is V2, which is equal to V2, will be equal to V battery, and V battery is constant. So by changing R1, yes, the value on each voltmeter will not be changed. Okay, so in this particular case, when R is equal to 0, V1 will be equal to V2, and each one of them will be equal to V battery. Okay, and since V battery is constant, so V1, V2 remain unchanged when R1 is changed. Another example, what would happen to the readings on the voltmeter if R1 was increased? Your attention, please. The most important thing is to determine what actually the voltmeter measures. It measures the potential across R2. In front of you, the voltmeter shown in front of you on this particular case measures the potential across R2. Okay? And it depends, it is equal to I R2. R2 is constant, so it depends on the current. It is proportional to the current. Okay. The voltmeter actually reads the voltage across R2. The reading of the voltmeter equals I R2, as I said. When the value of R1 is increased, the current decreases. So the reading on the voltmeter, which depends on the current, yes, decreases as R2 is constant, unchanged. Okay? So when R1 is increased, the current decreases, V1 decreases. Another example, what would happen to the readings on the voltmeter and the meter when the switch is closed, key 2 is closed. Okay, when the switch is closed, we are disconnecting R1. The resistance, denoted by R1, is eliminated, removed from the circuit. Okay, so we are decreasing the resistance. So the current must be increased. So reading on the ammeter should be increased. And what about the reading on the voltmeter? The voltmeter reads the terminal voltage. Okay. And what about the terminal voltage? Okay, it is inversely proportional to the current. The current increases, terminal voltage decreases. Okay, let me say it again. V decreases, reading of the voltmeter decreases, but reading of the meter increases. Once again, when the switch is closed, we are actually disconnecting R1. Okay, so we are decreasing the resistance. Current increases. When current increases, terminal voltage decreases. This way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.